how to like I don't yeah how to better show your work like for especially for word problems. So you know how the first part was solving equations, that was pretty okay for most of you, but for the word problem I think you guys can do a better job of showing like just presenting your work. So yeah, so just briefly talk about this first. So one of the key things is to write from top to bottom, and then left to right. And as I'm writing all these, I'll actually choose a problem from the homework and show you what I mean. So let me just say uh, this one. Oh wait, no. So number 10 from the homework. Uh, ac- actually, number 11. Yeah. So the last question on the homework. Well, some of you did it, and that's good. You guys got the right answer, but I want to like show you how to better show the work. Yeah, so I'll do that. I'll show you an example after I write down all the tips. So and the other one is to show calculations on the side, not during the process. Not in the process. And I will show you what I mean later. And the third one is when you have to solve when you solve for unknown variables, write a less statement. And then the last one is to for word problems, uh, write an answer statement. Okay, so these are the four general ideas that I have in mind right now. And as you do your work, maybe you right, one last thing, and pretty important as well. Write neat. Yeah. So if you have a neat writing, your teacher is going to like the first impression will be really good on your teacher. So write neat. Always write neat. Actually, this is not such a good question. Let me use the uh, number 4 as an example. Yeah. So this question. So you guys done this and most of you got it right. So Cindy filled up his, oh, shouldn't be his, her gas tank after traveling 165 kilometers, blah, 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 blah. So the question is, how much further can a car travel before its fuel tank is completely empty? So by this is it should be a hint to you that you are solving for unknown variables. And when you solve unknown variables, write a let statement. So how you do this is so let x be uh, the distance car can travel before empty car can empties. So that's the last statement. So for this question, we only have to solve for one unknown. So um like x in this case is pretty clear what it is, but when you have a more complicating problems where you have many different unknowns, it's a really good idea to write let statement. So that x, that y, that z, and so on. So after this, so write from top to bottom, left to right. So if there is space, always just write from top to bottom. Don't write from left to right because it gets confusing. Like if you have a block of writing over here, and then over here, and then over here. Like you have all these writing over here. So it sometimes gets confusing whether you are going this way and this way, or are you going this way, and this way. So it gets a bit confusing. So if you have to do that, what I suggest you to do is after you write this, right, usually go from top to bottom first, and then draw an arrow to indicate that from this step, you go to this step. But if you have space on the paper, just go from top to bottom. Don't go from left to right. So this is a proportion question. So you can solve it like this. So 165 kilometers. Oh, actually, yeah. So distance over gas is equal to 165 kilometers over 3/8, right? And that is equal to, actually I don't need the units here, x. So we use 3/8 of the gas, so then what we have left is 5/8 of the gas left. So then now we do the cross multiplication as I was talking about. So that times that. And then we have 3/8x is equal to 165 times 5/8. So now, so right now, I think some of you I see, you would do this here. So you would write like, you would, and then carry the 2 over, so 2, 3, and then 8. And then from here, you go 3/8x is equal to 825/8. So the problem with this is that you kind of interrupt your flow of idea. And as you, the person doing it, you might get confused about it, and then the person marking it will definitely get confused, right? There's suddenly like a work calculation there. So what I would do is on the side over here. So on the side, it can be the left side or the right side, doesn't matter. Draw a dotted line. And then over here, you do your calculation. So 165 times 5. 5, 2, 2, 3, 8. And then with that number, you just go back to here. You just directly use it. And then you can divide 8 on both sides. And then, oh, I mean multiply by 8, never mind. So multiply by 8 on both sides. And then I get 3x is equal to 825, and then x is equal to 275. Yes, that's the answer, I think. So this is a word problem, and we just found out what x is. But then now, so at the end, we write, as I said, write an answer statement. So what I mean by that is so answer, and then, so complete sentence, okay? So if your English teacher is going to mark this, what do you think she or him will give it? So the car can travel another 275 kilometers. Okay. So to recap, first I wrote a let statement. So let x be the distance car can travel before gas tanks empties. And then I did the work here. So distance over gas is 165 divided by 3/8 equals x divided by 5/8. And then I carried on to solving this equation. And when I need to show the calculation, I write it on the side. Oh yeah, and this one too. So yeah, I can do it here. So 2, 5. So 2, 6, 22, 7, 21, 15, and that's 5. So I show the calculation on the side here. And then I just get the answer, and then at the end I write an answer statement like that. So like if you show your work this way, like from top to bottom, and then write neat, like your teacher is really going to have a good impression on your work, and she's not going to be searching all over the place for your answer or like for where your work is. And even for yourself is really nice, because I saw some of you, you got the right answer, like X, you got X, and it's not only for this problem, other problems as well. But then because it's like all over the place, like something here and then there's a work there. So when you like write your answer at the end, you you got the right answer, but then you probably like misread it because of the messiness, and then you put down a different number, and that is very unfortunate. You got the right answer, but your answer statement is wrong, and that means your whole question is wrong because your answer statement is wrong. And always just write neat. And yeah, so I think my writing is pretty neat. So doesn't have to be like this, or it would be really good if you can write like this. Some of you have really neat writing, and that's really good. But like if you don't think your writing is that neat, just try to be, and just putting in the effort goes a long way. Like yeah. So that is about it. Oh, and like sometime another thing that maybe I should point out is when you have a page, right? And the question is here, so number 4. So that's the question. And then maybe over here, number 5. There's another question. Well, so the teacher gave you this much space to do it, to show your work. So ideally, you should be only using this space over here. So like, yes, sometimes like you have to write a lot, and you might have to use a separate page. But when the teacher like write the question, the teacher most likely gave you enough space. So if you have to use extra space, that either means you're doing the question wrong, or you're not or you're not showing your work neat enough. So, or like you're showing extra things. So extra things that you don't need. So while you have to show all your work, you have to try to keep it concise so that it just fits into the space over here. Okay? Any questions? No questions? Okay. Then I guess we will move on to the actual lessons for today. So, yeah. Inverse proportions. So last day, we looked at direct proportions. And if you still remembers what direct proportion is when one quantity goes up, the other quantity goes up. But for inverse proportions, it's exactly the opposite. So a relationship where two quantities have constant product. So, so a product is when you multiply two number and then you get the, yeah, multiplication is product. Is called an inverse proportion. So the key is constant product. So why is this important? Well, when you have a constant product, when one quantity goes up, the other quantity goes down. So if you can imagine, right? So an example is, so example, if you have a rectangle with constant area. So if you can still remember from last class, constant means always the same, right? So the formula for the area of a rectangle is length times height, right? Length times, length times width. Yeah, length times width. And let's say it's equal to 40. Now, in this case, the length and the width is inversely proportional, we say. Inversely proportional. So, like, if you can imagine when the length goes up, the width will go down. So let's say I multiply the length by 2. So 2L. Well, in order to keep this 40, I have to divide the width by 2. So the 2 here and the 2 over here cancels out, and we are left with L times width again. And that is again equals to 40. So so that's the property of an inverse proportion. When one quantity goes up, the other property goes down. And then when you multiply these two quantities together, they always get a constant product. So remember for direct proportion, it was they have a constant quotient. So that means when one quantity goes up, the other goes up as well. But this one is the two quantities are exactly the opposite. So how we write this? There's actually a way to write this. So first I'm going to, I didn't show you this for direct proportion. So direct proportion, we write it as, so let's say I have a value A, and if it's directly proportional to B, we use this symbol over here. A is proportional to B. And then when you write inverse proportion, so if A and B are inversely proportional, then we say that A is, and then this symbol is proportional to 1 over B. So that's the difference. So yeah. So any questions so far about inverse proportion? So this is kind of the definition. So two things that you keep note of is this. So yeah, the constant product, and then when one quantity goes up, the other quantity goes down. So those are the two key properties of inverse proportions. So then, well, maybe let me give you some examples of inverse proportions to let you have a better understanding of what it is. So one example, I don't know if you guys have studied history, but after World War I, Germany lost. So Germany lost and have to pay reparations. And what reparations means that uh like giving money to the countries that won. So yeah. So they have to pay reparations. But so that's a huge amount of money. So huge. Oh yeah, it was pretty huge. I forgot what the amount was, but so they didn't have so much money. So what they did, uh, didn't have enough money. So they printed money. Because after all, right, money is just paper. So like you just print more paper out and then you get more money. Well, no, that's not how it works. Because the country has approximately the same um I'll say wealth. Although that's not very technical, but like you get what, like I think you guys get what I'm saying. So like when you print more money, like food doesn't just come out of nowhere. Like the amount of food, or like the number of products, like steel or like all those kind of stuff, they remain approximately the same, right? So then, more money causes the value of each causes the value of the currency goes down. So in this case, the amount of paper money that they actually have and the value of the currency, they are what we call inversely proportional. And that is because the the country itself, the wealth doesn't increase. The wealth remains constant. So so goes up equals a value of money go down. So that is why printing more money is not good. This is what we call inflation, if you guys heard of that word before. And then like other things are like so like I won't write it down, but like when you have like every day you only have 24 hours, so the different activities you do each day, the time spent on each activity, they are inversely proportional to each other. Because you spend more time doing one activity, you have to spend less time doing another activity. So yeah. So if we go back, and then another example is like just the length and width of the area, as I talked about here. Another example. So if we go back to math now, so I say uh, x and y are inversely proportional. I'll just write IP. When x equals 10, y equals 6. So the question is, what is x when y equals 4? So I want you guys to try this question out. Pretty basic. And just remember the basic properties of inverse proportion. Constant product, and when one quantity goes up, the other quantity goes down. So this question over here. And if you don't feel like speaking up, just type it into the chat. Eight. Okay. Why 8, Emma? 12? Well, we are here to learn then. So 12. Okay. Well, why 12? Yeah, why 12, guys? Yeah, okay. when one side goes, uh, oh, okay, but then remember, it's the constant product. So by constant product, I mean like when you multiply them together, the value is going to be the same value when I multiply them, not when I add them. Does that make sense? So like if the answer is 12, right? Then what happens is so if x is equal to 12 and then y is equal to 4, then x times y is equal to 48. So 12 times 4 is equal to 48. But then if you look over here, 10 times 6 is 60. So these two are not equal. 15? Oh, Chloe, were you typing something? Yeah, 15 times 4 is 60. Yeah, so yeah, the answer is 15. So James is right and Chloe is right as well. So the answer is 16. Oh. So first we have to find the constant product. So the constant product is 10 times 6 is 60. And then we simply substitute y equals 4 into, so, and then x times y is 60. So then x times 4 is 60. So x is 15. Yeah, 15 is the correct answer. So with proportion, we don't like to add and subtract. The reason for that is because, so like when we multiply and divide, right? What we can say is that is 2 times the value of that or half the value of that. So for example, when y go from 6 to 4, that's the same as, so it decreased by, well, no, okay, let's say, not 4, let's say y is equal to 3, right? Then what we have is that y is divided by 2. So y is 1/2 of its original value. So when we have 1/2, then we can say that x will simply increase, will simply doubles. So that is why we, like in proportions, we like to use multiplication and division, because we can say that it is how many times of the original value. So I guess yeah, so like for example the actually I'll just give you another example. So if the area of a rectangle is constant and is becomes 3 times, so 3 times longer. What happens to the width? So try this question out. So yeah, just again type it into the chat. So what happens to the width? So like the answer should be how many times longer or how many times shorter, like something like that. So is it one half the length, or is it 2 times the length, or 3 times the length, or something? So it's not an actual value. It's just like how many times longer or shorter. Just that. Nobel, any idea? Or James? Okay, it's okay. How about Chloe or Emma? Don't know. Okay, it's okay. So maybe I'll go over it again. So, so the area of a rectangle is length times width, right? Length times width is equal to k. Yeah, so now, like, yes, the thing with proportion now is that you have to get used to the idea of having a constant. And like k here is like not a variable per se. It just means like a value, a constant. So uh, k can be 40. So, or maybe I'll just write 40 here. So as long as it's constant, it is okay. So constant, so it's 40. So length times width is always 40. So now the length becomes 3 times longer. So what does that mean? That means it becomes 3L, right? 3 times L. But remember that is always equal to 40. Length times width is always equal to 40. But if I just do this, 3 times L times W is equal to 3 times L times W. And what is this equal to? Well, this is the same as this, which is the same as this. So what we have here is 3 times 40, and that is equal to 120. But then that's not good because we say that the area is constant. So the area is always 40. So we have to do something to the width to make it back to 40 again. So what do we do? Well, so you know how when you have 3 times 1 over 3, you can cancel this out and it becomes 1, right? Or 2 times 1 over 2, that's equal to 1. 1, 5, 6, 7, 4, 3, 9 times 1 over 1, 5, 6, 7, 4, 3, 9. As long as these two numbers are equal, the answer is always 1. So then when we multiply by 3, if we divide the width by 3, then we essentially cancel this out, and we are left with L times W again. And when we are left with L times W, that is equal to 40 again. And that is the same as that. So what do I have to do to the width? Width divides by 3. Or another word, let me just erase this first. Width is 1/3 the 1/3 the original length. So when the length becomes 3 times longer, then the width has to be 1/3. So 3 times 1/3, that is equal to 1, and you're back to L times W again, and that's equal to 40. Does that make sense? Yeah. So Chloe, so because so this has something to do with substitution actually, and I'll go into that someday later. But essentially, when you say that L times W is equal to 40, you're saying that these two things, so the one in the yellow is equal to the one in the green, right? So when you times something by 3, and then you want this, and then times like a number, like some width is equal to 40. So when we substitute this in, so the green, right? 40 is the green. So the green is exactly equal to the yellow. So we can say that 3L times like a width, something here, is equal to L times W, right? So we don't know what this number is. But then, so 3L times something W is equal to LW. Now what we can do is we can divide L on both sides, just like solving an equation. Oh, divide L on both sides, and divide W on both sides, just like solving an equation. And we get 3 times, we don't know what this is equal to L divided by L is 1, W divided by W is 1. So 1 times 1 is equal to 1. So what is this question mark over here? Well, I was previously showing you that this would be 1 over 3. So 3 times 1 over 3 is equal to 1. And now what do we have here? Again, by substitution, this question mark over here is just is It is exactly this 1 over 3. And again, this purple, by substitution, is this. So it's 1 over. So width divided by 3. Well, that is the. So 1 over 3 times W. That is the same thing as saying W divided by 3. Does that make sense? Maybe? Maybe not? Maybe. Well, maybe, how about this? Instead of, let me show you another number example, like an example with number. So say, so the area of a rectangle is 60, okay? 60. I will redo this whole question. So the area of a rectangle is 60. Length is 3, and width, so the width would be is 20. So 3 times 20 is equal to 60. Now the length becomes, let's say, 4 times longer. What is the width? So it's pretty similar to the one before, except now there are numbers involved. So you can actually find the numerical value of the width, like what the width is equal to. So try this out. Yeah, well, Emma, when you get to a higher and higher level math, you realize that it's not an actual math course. It's a Greek letter, like a Greek language course. Right now, you're only seeing the alphabets. Wait until you get theta, or alpha, or sigma, or tau. All those fun, well, not really fun stuff. So. And all these have meanings, by the way. So, width is 5? Yeah, yeah, width is 5. Oh, what are those symbols? They are Greek letters. So, theta means an angle. And then this here is something called a tangential, tangent, I don't know how to pronounce it. Acceleration. It's a physics. And this here means a sum. And this here is torque. And yeah, you'll learn about it later. But oh, come on, Emma. Don't dislike math. When you get the hang of this, it's fun when you get the hang of it. Just in the beginning, it seems hard. Like everything in the beginning will seem hard. So, oh, yes, the answer. Yes, so for this question, the answer is 5. So yeah. So again, so when I can solve this equation, so the length is 3, and then when the length becomes 4 times longer, it becomes 12. So length times width is 60, and when the length is 3 and then it's 4 times longer, it becomes 12 times W is equal to 60, and then width is equal to 5. Or the other way, as I was saying, when the length becomes 4 times longer, and in order for the product to be keep the same, the width has to be width divided by 4. And then so it's 20 divided by 4 is equal to 5. Yeah, so you could solve an equation, but yeah. So any questions? Oh, Chloe is typing. That's right. Do you have a question, Chloe? You were typing. Oh no, it seems like you are typing, so then I thought you were going to ask a question. So anyway, okay. So I guess actually let me redo this in a way that will maybe allow you to understand the idea of multiplying by 4 and dividing by 4. So the original is 3 times 20 is equal to 60, right? So now the length becomes 4 times longer, so I'm just red. So 4 times 3. Now the width is going to change. So I'm going to let that change be x. So I'm going to say x times 20 is equal to 60. So now I can divide by 60 on both sides. So divide by 60 on both sides. And we have 4 times x is equal to 1. So x would therefore be equal to 1 over 4. So this here, so it's 1/4 of the original length. So 1/4. And I guess another way that we can put this is that this, we call it a factor of 4. So yeah, a factor of 4. Maybe you guys have heard this. And then what this is called a factor of 1/4. So I don't know if that will help you guys understand it better. So when we say when it doubles, it's increased by a factor of 2, or when something is tripled, then it's a factor of 3, or if something is halved, so 1/2 of its original, then it's a factor of 1 over 2, a factor of 1 over 3, something like that. Okay, and when and then again, as I was saying, when you have 1 over 4 times w, that is exactly the same as w divided by 4. So that has to do with fractions, right? So something fraction times this, you just put it in the numerator. So w divided by 4. Let me give another example then. So, rectangle again. Rectangle again has a constant area, okay? So I'm gonna challenge you guys to not use numbers, instead use a concept. So constant area, so what does this mean? Always the same. The area is always the same. So the length times width is always equal to the same thing. When length is increased by a factor of 3 over 2. What factor does the So I want you guys to try this out again. So the length is increased by a factor of 3 over 2. So not a whole number, but it's still a number, 3 over 2. So what factor does the width changes by? And again, constant area, so it's inversely proportional. Good luck. Any ideas? Nobel? Emma? Chloe? James? Good. Yeah, take your time. So maybe a hint for you to maybe something to help you do this question is you can imagine different numbers. So you can like, although I didn't say what the area is, like you can put down like 60, you can try 60, or you can try 30, it doesn't matter. So you can try out a number. And then for the length as well, you can so you can try 5 or maybe 6. Yeah, you can try 6 and then see what happens. Does that make sense? So I didn't give you any specific value, but then you can always put down specific values yourself. So no idea. It's okay. Oh, James, you're getting something? Oh, Emma? No? Yes? Yeah. Okay. Um, so I will go by what I talked about, so I didn't say any, I didn't give you any value, but so to try out different values, okay? So I'm going to say that the rectangle has an area of 60, and that is not going to change. And I'm going to say that the original length is going to be 6, okay? So 6. So that means, so conditions I assume. So I'm gonna assume area equals 60 and then length equals 6. So then that means the width is equal to 10, right? So 10 times 6 is 60. So now, so when the length increased by a factor of 3/2, so length, length multiplied by 3/2 is equal to 6 multiplied by 3/2, and that is going to give me 9, right? So what's the width going to be? Well, length times width is always going to equal 60. So then length is now 9, so 9W is equal to 60. So then given these conditions, right, these assumptions, we find that W is equal to 60/9, or since I can simplify it, that is gonna give me divided by 3. So divide the top and bottom by 3, 20/3. Okay, 20/3. Now, so the original width is 10, right? So this is 10, and then new width is 20/3. So you know how so a number times a different number is equal to another number, right? So if I say that the original is 10, and then multiply by a factor, this is the factor, because we want to find out the factor, is equal to the new width, so it's 20/3. So essentially we're just solving an equation. So the factor is equal to 20/3 divided by 10. So divide 10 on both sides. So the factor is equal to 20/30, and that's equal to 2/3. And that's our answer. So I assume that these are the conditions, and then I figured out what the new width is. And then with the original width and the new width, I figured out the factor. Does that make sense? Kind of, maybe? Or not at all? So yeah, inverse proportion is harder than direct proportion. I gotta say, like understanding this concept is harder. Now, see, I was going through all these examples, right? And it seems really frustrating sometimes how to find out like So what is the width? Like, so like the factor, find out the factor. But uh, it's actually really, really simple. The pattern, when you find the pattern, is really simple. So if one quantity is increased by 3, so this is 3 over 2, right? Then what you should realize is that the other quantity is exactly flipped over, the top and the bottom, see? 2 over 3, 3 over 2, 2 over 3. And then this one, the length becomes 4 times longer. What becomes of the width? 1 over 4. Well, 4 is because 4 is essentially equal to 4 over 1, right? So then the other one is just flipped over, 1 over 4. And then, yeah, so it's actually really simple. But the reason why I didn't tell you guys this is because I don't want you to just like notice this pattern. I want you to really understand what it means by how to find it out. Because yeah, like I really want you to find like figure it out. So like when you do a question, I guess you could just use this pattern. It's flipped over. But while you are using this, I really want you to like think about it, ponder on it, what this flipping over means. Okay? So if you are not comfortable, think. It's all about thinking. So um I guess another example then. More example the better. So you guys get more familiar with it. So x is, so still remember what this means? Inversely proportional. Uh, so try this out again. So again, think back to the properties of inversely proportional constant product. It's pretty much like the first example we did. So try this out. Oh, and why is that? Yep, 2 times 12 is 24. Yep, yes. Oh, the fancy typing again. Yes. Yeah, good job, guys. It is. So again, the first we have to find out the constant product. is 4 times 6, 24, and then xy is equal to 24. So then when x is 2, 2y is equal to 24. So y is just 12. Okay. Here's another one. Y is inversely proportional to x. So when x is 3 over 4, y is 5 over 2. So what is and y is 1 over 8. So here. So what's the answer? Any ideas? Chloe? Emma? James Nobel. So this is actually exactly the same as the last question, except the numbers are different. Does that make sense? Only the numbers are changed, but how you do it is exactly the same as the last question. So yeah, I guess I would. So I think what messed you guys up is the James is typing. Okay, no, it's okay. So I think what messed you guys up is this one, right? So usually I write x is proportional to 1 over y. But then the thing is, these are just letters. They represent like yes, they represent value, but they're just letters. So I can just change this to y, and then this to x. And exactly that? Isn't it just like this? Except the letters are different. I mean, they're the alphabet. Like some people thousands of years ago decided that X comes before Y. But what if in our alternate universe the alphabet actually goes Y X Z? Like it's just the letters are different, but the math is the same. So first you find a constant product. So the constant product is 3 over 4 times 5 over 2. It's fractions, but you can still multiply them. It's equal to 15 over 8. And then they are inversely proportional, right? So y times x, well, y times x is exactly the same as x times y. So y is inversely proportional to x. Is the same thing as saying that x is inversely proportional to y. So equal to 15 over 8. So then 1 over 8x is equal to 15 over 8. And when I multiply both sides by 8, I get that x is equal to 15. And it's as simple as that. Right? Not much different, except the numbers are different. Does that make sense? It doesn't matter what the letter is. And again, so x is proportional to 1 or is inversely proportional to y. It's the exact same thing as saying y is inversely proportional to x. Yes, I guess keep this in mind. And actually the same goes for direct proportion. Like x is proportional to y. It's the same thing as saying y is proportional to x. They mean the exact same thing. So I'll highlight this. Okay. So that is it for today.